Alright, this is turning into a Friday the 13th situation. We're up to part 3 now. I wanted to give you a little postlude to the forward dynamics derivation we did. In the first 2 parts, I'll take you for a quick tour through the code. This is SliderCrankMuSim. This is the mothership where I define some integration tolerances, and then I call my function which calculates the derivatives. And that function is called SliderCrank_mu. We're going to simulate the slider crank motion for 10 seconds, and we're going to start the slider crank from a crank angle of 45 degrees. I think the crank length was what? The crank length, that's got to be in here somewhere. Where did I define all those geometric? Okay, so the crank length is 0.2, which means half the crank length is 0.1. So if I start the crank at 45 degrees, the x and the y initial positions are 0.0707. Now when you start a mechanism like this at a funny angle, you're going to have to do a little bit of trig to figure out your initial angles of links 2 and 3, and you're going to have to try and figure out your initial displacement of the slider and so on. So this is a set of initial conditions. We got 14 state variables. These are more or less compatible. This is actually the initial positions of all the links. All the velocity initial conditions are 0. We're going to start this from rest. We're going to apply a torque and see what happens. Inside the slider crank mu function, we take our 14 state variables and we give them intuitive names. So xg2, vg2x, yg2, and so on. I'm going to set the viscous pin friction to 0. I've actually got 2 different... Okay, sorry. I have viscous pin friction coefficient B. We used to have a bit of trouble putting in the mu n friction for the block in the slot. So we kind of had to use viscous sliding friction instead of mu n, but we finally figured out a way to get the mu n to work. And we'll touch on that a bit further down. I declare my masses, my inertias, my stiff spring stiffnesses, damping rates. The crank is 0.2 meters long. The connecting rod is 1 meters long. Mu is 0.2. G is G. I'm going to put a torque of 10 on this thing and see what happens. Now if I torque up a slider crank that doesn't have much friction in it, what should happen? I guess it should just start going faster and faster and faster. But if I apply a constant torque, as we know from our engine shaking force analysis, the torque it takes to drive a slider crank at a constant speed is up, down, up, down, up, down. So if we apply a constant torque, our speed is going to be up, down, up, down, up, down. So we'll see what the plot for speed looks like at the end. First thing I do, my function has received an x vector with 14 state variables. First thing I'm going to do is I'm going to take those and I'm going to define my spring displacements and velocities, and then my constraint forces. I do that for the springs at A, the springs at B, the springs at C. Here's the algebraic relation that gives me the normal force between the slot and the block as a function of F43Y and M4G. So now I got that. I can use that to find my friction force. So my state derivatives, these are Newton's laws. There's some of the forces in the x direction is ma for link 2. Here's one of my big old torque equations. Okay, so I've got 14 of these first order ODEs. I stop after 12. I leave the block ones for a second because I got to define the friction force. The problem with using mu n is that friction force, well, what happens if I plot the Coulomb friction force, the mu n friction? The Coulomb friction assumes that the friction force doesn't depend on the velocity. So let's see. Here's a plot of friction force. Here's a plot of velocity. Friction force is mu n if I'm going one way, and it's minus mu n if I'm going the other way. And when you switch directions, the slope of that friction function is infinite. There's a discontinuity. And numerical integrators don't like discontinuities. In fact, this is an oversimplification of an oversimplification, because this doesn't take into account that really there's a static friction force that's a little bit higher than your kinetic friction force. So this curve should go up and then come down. That's hard to deal with if you're a numerical integrator and you're trying to find a time step that's small enough to capture your slopes when your slope is infinite. The only way we found we could make mu n friction work in the context of a Matlab simulation with ODE was to smooth out this a little bit. Not have an abrupt transition from minus mu n to plus mu n, but just sort of smooth it out a little bit. We can make this pretty steep as long as it's not infinitely steep, and that'll make the numerical integration a lot more stable. So I took a simple shareware curve fitting program, and I put in a bunch of points that gave me this desired shape. And that curve fit algorithm, it was called Curve Expert, it told me that I could get that shape using this kind of an exponential. Let me zoom in a little bit on this. Okay, here's 2 over 1 plus e to the minus 10v minus 1. It goes from minus 1 to 1. And if I change this parameter, if I change that from minus 10, if I change that from minus 10 to minus 1, and I redo the plot, I get a lot softer transition. So if I tweak this parameter, if I make that a high negative number, I can get something that looks close enough to my desired Coulomb friction law to work. So I'm going to use that in the code. If I go back to the Matlab code, here's my patch to make the friction force not numerically unstable. I define the sigmoidal function, 2 over 1 plus e to the minus 10v minus 1. What v am I interested in? I'm interested in the velocity of the block, which is vg4x. So this function goes from minus 1 to 1. So that's going to do the same thing as if I use the signum function, except it's going to do it in a continuous instead of a discontinuous way. My friction force is now mu times the absolute value of f14y times this function with the exponential. Okay, so that smooths things out and makes the numerical integration possible. After I define ff, or f fric, I can then use it in my final f equals ma equation for the x motion of the block. Alright, when I run the code, what do I get? It took me 11 seconds to simulate 10 seconds of motion. My crank length was 0.2. That means that xg2 should go from plus 0.1 to minus 0.1 to plus 0.1 to minus 0.1. So xg2 is moving back and forth between the expected limits. And yg2, the same thing. This point g2, that's moving in a circle. That's a point in the middle of the crank. Now it looks like the up and down peaks are getting closer and closer and closer together. So it looks like with this constant torque, my mechanism is speeding up. It's getting faster and faster and faster. There's some friction in here. I didn't put the viscous pin friction in, but I put a little bit of mu n friction in there. So eventually this thing should reach a steady state velocity. If I put the viscous pin friction in there, it would more quickly get to a steady state speed. Here are xg3 and yg3 along with theta 3. Theta 3 goes from plus to minus, looks like about 17 degrees. That seems like it might be okay. Quick kinematic analysis would tell you if that was right or not. The range of travel of the block is 0.4 meters. That's twice the crank length. Okay, that pleases me. Here's omega 2. We supposed that because we were applying a constant torque, we would get a non-constant crank speed, and we do. Here's the crank speed getting faster and faster and faster, and here's a significant speed ripple. As we know from engines, we have to apply a varying torque if we want to get a constant crank speed. So here's the crank speed rippling. The way to smooth that out would be to add a flywheel. How can you simulate a flywheel? Well, you just put a huge rotational inertia onto link 2, and if the inertia of link 2 is huge, our 10 Newton meters of torque is not going to be able to accelerate and decelerate the big link 2 inertia this fast. We're going to see the speed ripple get flattened out quite a bit. And that's one of the things that you have to do in the last part of your problem set 3. The joint deflections, they're getting up to around 4 millimeters after 10 seconds. And the crank length was 200 millimeters, so that could be a bit excessive. We may want to tighten up the spring stiffnesses. The joint deflections get bigger and bigger because the mechanism is going faster and faster, and the shaking forces are getting bigger and bigger. So there's your slider crank output, and that is it for the slider crank forward dynamic series. Promise.